Hello, everyone. Welcome to the first MultiScale Talk given by Dr. Maja Vuckovac. Maja is a research fellow at Aalto University in Finland. She has obtained her PhD degree in applied physics at the same institution. And today, Maja is going to talk about anomalous flow behavior of viscous droplet fluids. So, Maja, the screen is yours.
Thank you, Zoran.
Please share the screen first.
Yes, I hope that the screen can be seen now.
Yeah. Yep.
Okay.
Great.
Thank you for the nice introduction and good afternoon, everyone. I'm Maja Vuckovac, research fellow from Aalto University in Finland, from Department of Applied Physics, Soft Matter and Wetting Research Group led by Professor Robin Russ. And today I will talk about anomalous flow behavior of viscous fluid droplets. So as a title by itself says that we have some completely unusual behavior of a viscous fluid droplets once when they are placed in a super hydrophobic coated sealed capillaries. What you can see on the image behind as one of example is a honey droplet inside of this tube. Viscosity is quite very important physical property because it limits fluid flow and mass transfer. In a very simple word, it says the more viscous the fluid is, the slower it moves. And this is extremely important once when we are talking about the transport of the fluids through the from different industrial to biological applications and from different scales, like from the pipes and the microfluidic devices. Usually, the researchers try to improve the flow of viscous fluids by utilizing superhydrophobic surfaces. Those surfaces are known to be prone to repel the water in a way that once the droplet is placed on such surfaces, it will form the bead thanks to the special microscopic roughness that can be seen here. That there is kind of microscopic roughness, then the nanoscale roughness on top of it, and with a decent chemistry, which is a low surface chemistry. Once when the droplet is placed on such structures, the droplet will form the bead and can be easily moved. What can be seen on the video next to it, and the video doesn't want to show here, where actually the big amount of the water is placed, and this silvery reflection here, what can be seen is actually this trapped air called plastron. And once when the leaf is tilted, the amount of water will leave the leaf completely dry and clean. And thus superhydrophobic surfaces have a high contact angle, small contact angle hysteresis, and small friction and small adhesion, and the droplets are gliding very easily on top of such surfaces. So what we did in this work, we used commercially available superhydrophobic coating. It's called Hydrobead, and we applied in NMR capillary. So we coat it from the inside. And once when we place the droplet inside these tubes, if they are from the open ends, either the capillary is kept vertically like it's shown here, or under some angle, the droplet velocity will drop with increase of the droplet viscosity. This is very similar if we take a look how the droplets behave of different viscosities, how they behave actually on the planar superhydrophobic surfaces, so that the droplet velocity will drop down or decrease with the droplet viscosity. But once if these superhydrophobic capillaries are sealed from one or from the both ends, then droplet velocity actually increase with the droplet viscosity. And this is this counterintuitive behavior that the higher viscous droplets can move even the order of magnitude faster than the low viscous liquids. How this works actually? So we have a droplet in a tube, and then it behaves as a piston, so that the droplet is actually compressing the air below and force it to go through the tiny layer of air trapped around, so that it goes on the top part where the pressure is lower. Then we try to explain this anomalous behavior by just using slip-induced drag reduction for pipes where actually the friction factor is inversely proportional to the Reynolds number, what means that what you can see in this equation is that actually the friction parameter or factor will be directly scaled with the viscosity of the liquid. And this means that it will oppose more to the flow. So we will have smaller flow as the viscosity increase. What is not case in this system that we have here presented. Also, we try to see how here works this superhydrophobic surfaces use drag reduction, which here actually mainly come from the contact angle hysteresis, but it's independent on the fluid viscosity for this very slow quasi-equilibrium droplet motion. And pay attention that the droplet velocity here is in a scale of the micrometers per second. So it's extremely very slow. And then we show that there is huge dependence of the viscosity and even opposite from what we know before. We also try to see how actually the lubrication theory is working here, well known as Landau-Levitch-Bretherton or LLB theory, which in this equation here you can see how the thickness of the lubricating liquid or gas in our case is connected to the capillary number, where the capillary number is then the function of the droplet velocity, what we will have here as a central droplet velocity of the center mass droplet velocity. But once when we calculate this thickness of the plastron from LLB theory, we got a nanometer plastron thickness, while actually our experimental cases are in a micrometer, what we obtained from the AFM images, as you can see here. And then we assume that actually air is trapped in some average layer. So from actually the lowest, the protrusions like here to the highest peak, and then how the droplet sits there. Then experimentally, we try to really understand what guides this way of or this behavior of the droplets in these systems. So we try to eliminate the plastron, and this can be obtained by using hydrophobic capillary, so that we specially prepare hydrophobic capillary or the droplet in a Wenzel state in the exactly same superhydrophobic capillary, so that actually the droplet wets the surface roughness, and that actually accommodate the shape to the roughness, so there is no air trapped below. And we found that the droplet is not moving in this case, so that existence of the plastron is really extremely important in this case, in a way that there's no plastron, no droplet motion. Then later on, we look how the droplet velocity depends on the droplet length. And here we plotted droplet velocity versus the droplet viscosity for all droplet lengths. And then the only thing here with the blue squares, what you can see is extremely small droplets that are almost spherical shape. And if you remember from the previous slides, the droplet is a little bit squeezed in these tubes. So actually, when the droplet is enough big that it's squeezed in these tubes, the droplet velocity doesn't depend on the droplet size. Then later on, we study how surface tension actually guides this, because this was the first intuitive thing what we think maybe it's actually guiding this kind of droplet behavior. But unfortunately, once when we plot all these three systems, so we have three different systems of PEO, sucrose, and glycerol water solutions. And once when we plot them together in the master curve, they do not collapse together. So they behave as three different systems, which indicates that surface tension, yes, it is responsible, but it's not the key parameter. Also, once when we are plotting the density of the droplet, if we think that the droplet is guided by the gravity in these capillaries, then one can notice that actually they scale like, and they depend and increase with the droplet density, but also one need to have in mind that in our systems, once when the density is increasing, also viscosity is increasing. So further, to understand it a little bit better, we try to visualize the flow inside these two systems. And unfortunately, videos doesn't work in this presentation, but what can be seen from them is that for the low viscous droplets, the average internal flow velocity here is presented, and that means that the internal flow in the liquid, how these beads fastly rotates, actually show to be extremely very high velocity in comparison with the droplet center of mass droplet velocity. And center of mass droplet velocity is actually the macroscopical droplet velocity, what we see here, how the droplet by itself move. And the UD then is the flow of these particles inside it, which means internal flow. And we can see that for the high viscous droplets, actually, there is almost vanishing internal flow, and these particles are flowing together with the droplet down, and the velocity as viscosity increase, the velocity between them match each other. So also to just be sure that we didn't introduce any kind of additional flow, and that this flow pattern is actually just because of the system as it is. We also study the system where there is no plastron, so there is no air. And this shows that once when there is no plastron, again, here the existence of plastron is extremely important, which means that there is no flow of the particles. They are static there inside the capillary for a very long time. So further on, to just understand this droplet motion and to study the flow of the particles inside the droplet, or internal flow inside the droplet, we look at the internal flow, which is actually the viscous flow, as we are talking about the viscous liquids, which is given by equation where n is viscosity, A is area where this flow happens, and then dV by over dx is just the gradient of velocity in direction where the flow happens. And for our case, once when we put in our system with just taking account that we are talking about the liquid, so we have the droplet viscosity, we have the area where it happens, and then also we have the velocity over the radial distance, because that's actually how the flow here will be defined. And these droplets are driven by the gravity, so it's just the mass of the droplet driven by the gravity force in the gravity field. And then once from A and B, once when we equal these forces together, then we got the velocity profile for these internal flows inside the droplet. But one thing what can be seen from this equation one is that actually the velocity is inversely proportional to the droplet viscosity. So that means once when the droplet viscosity increase, this will slow down, and that's actually what we have. But we couldn't explain this for the lower Reynolds number, since there is some transition between turbulent and laminar flow, since we just assume that we have a laminar flow here. And this doesn't say that by the viscosity increase, we will have the increase of the droplet velocity, but it's a kind of a very good match of the droplet beads that are actually slowing down with the droplet viscosity. And this is what is for expected and actually what we knew already. But to explain on a general level why the droplet of high viscous liquid is moving faster, then we start thinking about the coupling of hydro and aerodynamic flows. So where actually we assume that in this plastron or the air layer that is trapped between this coating roughness and the droplet, air can move through it and then it flows upwards. And for this thing, we actually assume that both flows in the droplet and in the air are uncompressed. So we are talking about uncompressed flows. So then just knowing that the droplet is going down and the air is going up, we can then just from the conservation of the volume flow rates, got that for the droplet flow rate, it's just this equation. And then for the air, just for the boundaries where air is actually defined, and it will be more like a cylindrical ring through which the air will flow around the droplet. Then the equation looks like this. And then once when we equal, so what goes down it goes up, so that these two flows are equal, we can obtain the velocity of the air, since we are measuring the velocity of the droplet, and then based on it we can then just have the velocity of the air. Then we are looking what is the main dissipation mechanism that's happening in the airflow. So it can be inertial friction forces, which are given with just the gravity-driven forces, and then it's just defined by this equation here. And for this system, it looks this way. And then also viscous friction forces, where again we have the viscous dissipation, and then for the air, for this geometry and these like boundaries, it happens this way. And we need to plot this so to be sure which one is the main responsible. And here is presented where you see with the full red dots that it's actually the viscous dissipation, while the open circles are friction dissipation, and that viscous dissipation is dominating actually. So then we can say that our main dissipation mechanism in the air is viscous friction forces or viscous dissipation, which is given here, and then it's directly scales with the viscosity of the air, then the length of the droplet, droplet velocity, it's the radius of the capillary, and then this is the plastron thickness or the thickness of the air layer trapped there. And the pressure difference is the one that actually is guiding here, because I already said that the droplet is behaving as a piston and it compress air and then push it to go through the plastron upwards. And experimentally, we found that this is actually the hydrostatic pressure, which just is density, gravity, and the length of the droplet around which will this happen. And then just equaling these two equations from C and D, we got the droplet velocity, which then scales with the droplet density, gravity, the third degree of the plastron thickness, and then it's also inversely proportional to the viscosity of the air and the radius of the capillary. But to fit this data, we couldn't just get the perfect fitting if we are fixing the plastron thickness as we calculated from the AFM. So what we need to do here is actually we leave it as a free parameter, and then we saw that we can get the variation in it depending on viscosity. And we try to explain it, and we introduce here actual plastron thickness. So that means that we are allowing now the droplet to deform, so to the surface roughness, where our then plastron thickness will be dependent on the viscosity of the density and the surface tension. And this epsilon is actually here interface deformation, so the amount how droplets can penetrate inside the surface roughness. And just having the equation 2, which is given here, and if we look what is the constant in our system, so that we have now the same gas, which is air, we have the same capillary diameter, we have the gravity. So then we can fix for this side that we say that for the glycerol, it will be the thicker one. And then related, if we fix that one, that will be this value. And then later on, we can calculate numerically for each droplet viscosities or for all our systems, actually, what will be the delta or the plastron thickness now, that actual plastron thickness. And then the deformation can be also calculated based on this equation. And once when we plot, we have it for all viscosities to look like that actually the plastron thickness is thickening with increasing the viscosity. But since this is numerical calculation, we also try to just see how we can explain it like physically, what is the physics behind it. Then we try to model interface deformation as the growth of the fluid bump into the roughness. So as I already said, it's just the amount of epsilon, how much it can go inside this direction towards the coating roughness. And this really nicely follows Stokes' law, where delta P is the pressure gradient, and this is just the Laplace pressure of the bump epsilon, or the curvature of the epsilon in the direction of the tube diameter. And U bump is actually the velocity of the bump, so how fast it will grow inside over the scale of the roughness. So delta here is not anymore the plastron thickness, it's just the unit of the roughness features of the coating. And this all can happening only in a low time of experimental time scale, which here is defined how fluid with velocity UD, so this is now internal fluid flow, how much time it has to pass from one roughness feature to another one. And then based on these two equations, now when we know the time and we know the velocity of growing the bump, we can calculate how much this bump growth into the roughness. And then from ENF, actually, we can just calculate epsilon. And this is the equation which is given to us. And once when we are plotting now the epsilon calculated from equation 3 and also from this numerical calculation, what we already did, so we find that we have the perfect match between them. So that our theoretical scaling model can actually very nicely explain these physical phenomena, which means that the higher viscous liquids, they do not have time to just deform the liquid air interface, while the low viscous droplets, they have a time to deform liquid air interface and to penetrate inside the coating roughness, what will probably induce additional drag force, which will slow down these liquids. But since this is the theory, we also have just a quick proof of that by measuring it with confocal reflection interference contrast microscopy, where here you can see on A, when there is no nothing inside, so there is no liquid inside the capillary, we can see just reflection from the coating, and this looks like this in this image below. But once when the water droplet pass there, then we will have the interference from the glass coating and then also from the air liquid interface, and then this will together give the fringes interference patterns, which are for the water very densely packed, what means that what actually indicates that spatial variation of there is the spatial variation of the plastron thickness once when we are talking about water, and then this actually show us that the water is deforming interface where it really tries to accommodate the shape of the interface to the surface roughness. While for the glycerol, we see that these fringes are like sparsely, so they are kind of more thick and far away of each other, which is indicating that the plastron is constant in these cases. So it's not, as we assume as a theoretical model, it will be perfectly flat. It's sagging, but much, much less sagging, so that actually the plastron thickness is higher for the high viscous liquids. And then in conclusion, so that we have the droplet inside the sealed superhydrophobic capillary, and we notice that for these systems, the droplet velocity increased with droplet viscosity. We show that by theoretical modeling or scaling law that there is on the time scale of experiment, there is possibility that low viscous droplets can deform interface and then just accommodate the shape according to the roughness, while for the high viscous droplets, this is not the case. And that means that the high viscous droplets actually, they are gliding on much thicker air layer through these capillaries. And this is thanks to the viscosity suppressed deformation of the droplet air interface. And then also there is the special coupling between hydro and aerodynamic flows in a droplet and the air, which is trapped into these structures of the coating called plastron. And also we show for the first time here that actually plastron is not only improving the droplet motion in a way that it reduces the contact area and friction, but it also have very important role in controlling fluid flow, like making high viscous liquids to flow much faster than the low viscous liquids. Yeah, thank you. That will be all.
Awesome. Great work. Can you still share the slides? Because I have a couple of questions.
Yes, very high.
So I'm actually interested, how did you manage to remove the plastron? I think slide, 7. Yeah, so how you have a super hydrophobic coating within the capillary, and then how do you remove the plastron?
Well, it's just the mixture of ethanol and water, since then the surface tension will be lowered down enough that it can go into the coating roughness.
Okay, well, nice trick that I was not aware of. Okay, well, I have actually written some other questions here. So you said that you're using a Hydrobead as a super
Yeah.
hydrophobic coating.
Yes.
So have you guys tried some other super hydrophobic coatings?
Yes, I didn't put it here, but we try Glaco. This is so Hydrobead. It has the surface roughness on a micron scale, while the Glaco has on the hundreds of nanoscale. So it's slightly like less roughness, but we noticed exactly the same behavior. But it's just like that you need to wait a days. So that the thickness of plastron is very small, so you need really to wait a long time that you see the effect, but it's still there. The glycerol was moving, or high viscous liquid was moving much faster than the water droplet.
Okay, good. Actually, I have only one more question because the presentation was that clear that it didn't leave too much room for questions. So do you have any idea whether this, because this is really basic research, whether this kind of, I don't know how to say, this phenomena can find applications, like let's say some, kind of practical or industrial related applications or something along those lines?
Yeah, it's really like very, as you said, very basic research, and it's really very nice physical phenomena. The real applications are quite tricky. If we take a look, it's micrometers per second. So who needs that? Maybe in some microfluidic devices where you can control the difference of the pressure from both sides, where you can actually guide them on extremely with extremely small speeds to have like these chemical reactors. That something is like reacting one solution with another, like mixing of the solids of the solutions, something like that. But that's kind of one in microfluidics application. Another one is where I personally see it. I do not know how useful it is. If it is also biocompatible, then, for example, in these infusion systems, and when people are very ill in hospitals and they need these kind of things drop by drop, so that it can go in that way.
Yeah. Okay, that's all. And then I hope the viewers of this presentation are going to be happy and enlightened about this new physical phenomena. And especially this is very good for the geeks working on wetting and soft matter physics. So thank you again, Maja.
Thank you.
And I am looking forward to invite you again on to present some of your other works again in the future.
Yeah, thank you.
Okay, bye-bye.
Bye.